So let's start. So we discussed about RIP in the previous lecture, as you may remember. And now we're going to discuss about OSPF, which is much more popular for multiple reasons. And you may remember that one of the reasons is a convergence. So that's the reason you should understand what is a convergence. It's really important for a routing protocol. And what is more is really important because of the routing policies. So we're not entitled to one choice, which is counting the number of hops. We can do better things than what we can do with RIP. So that's the two main reasons why it's so popular. So let's talk a little bit about those approaches, which called link state. Link state approach. So once again, it's based on the Dijkstra algorithm. So for those of you who haven't yet studied the Dijkstra algorithm, I'm going to show you how it works. But basically, it's about visiting some nodes in the graph and being able to discover the shortest path. So anyway, so there are a couple of things here, even though mostly this is related to the protocol. So regarding the protocol itself, so first of all, any router needs to know their neighbors. So as you may see, this is the same with RIP. I don't discover who are my neighbors, the direct neighbors, the adjacent neighbors. No, we need to configure them manually. So it means that the routers, somehow, we need to give them the IPs of their neighbors. All right. And what is more, you need to know the cost as well. So that is something that I need to manually configure. So I need to know the cost of the link to my neighbors, what is the IP of my neighbors, and then the only thing that as a router I need to do is to check what is the state of the link, if it's up or down. And this I need to measure. So this, spoiler alert, that will be what we call the hello messages. So we'll see that we have specific messages which are here to tell us if my neighbor is up or down, either because my neighbor have crashed or because the link is down. All right. So we have messages for that special purpose. On top of those messages, we have what we call the link state packets. So the link state packets is basically a packet where I'm going to list all the links to my neighbors. And now we're going to indicate for those links, who is my neighbor, what is the cost, that is a manual cost, plus what is the status. And this packet, listing all the links with my neighbors, with my direct neighbors, this is something that I'm going to flout in the network. So this is not like a distance vector that I send only to my direct neighbors. That packet, right, need to be sent everywhere in the network. So any router keep track of the link to their neighbors, tell what is the status of the link, if it's up and down, and needs to summarize all this information regarding all the links in the link state packet, and that you will basically flout or broadcast everywhere. All right. So the broadcasting here, flouting, is either periodic. So we need to do it periodically. Hopefully it's like somewhere around every half an hour. So we don't need to do it every minute or every 30 seconds, such as RIP, hopefully. Only 30 minutes, but of course it's also triggered by an event which indicate that the topology have changed. So let's say if the state of the link is up or down, or if the costs have been changed, or if I'm not receiving any hello messages, right? That will trigger a broadcast of the link state packets, right? So either because the link is down, or even if I repair the link and it goes back up, I need to broadcast again. So you see, so broadcasting here is not only because of bad news, also good news, okay, will basically have the same effect, right? So it's not only because of failures and bad things, it's also for good things. So as I said, link, failure or repair, a router have crashed, one of my neighbors have crashed or have been rebooting, so it's back up again, or if the admin changed manually the cost of the link. All right. So why do we need the link state? Because let's say if as a router, I hear about all the other routers in the network and they tell me about their neighbors, I would be able to create locally a database where I'm going to store the topology of the network. So that database So this is the LSP packet, link state packet. This is a database, the link state database. All right. So you understood that in order to run the algorithm, the Dijkstra algorithm, I need to know the complete topology of the network. And that is a big difference compared to RIT. You remember RIT, all I need is the vectors for my neighbors. And the vectors is just like some distances regarding some destinations. Here, no. I don't trust anybody. I need to have my own database. And based on that database, then I can run the algorithm. And the algorithm, in the case of Dijkstra, we need to know the end-to-end path, which means the detail of all the hops of one path, such as I can extract the next hop and put it inside my table. So you see, so it means that here I need a lot of CPU. Here I need a lot of memory for the link state. And since I'm doing broadcasting, I need a lot of bandwidth. Bandwidth, memory, CPU. So it needs more resources than RIP. But that's the reason we can achieve a better convergence, right? Okay, so let's get a little bit more into the details. So once again, let's put Dijkstra out of the way because it's not the main concern. But basically, it's also an iterative algorithm, which means that we need to run like a kind of a loop, right? And the loops here that we're going to have, the iterations, they are about visiting, okay, some nodes. So it means that on my local topology, I need to inspect all the nodes that I know, all the routers and destinations. And at each of those iterations, whenever I'm visiting someone, it will give me the shortest path to that guy, okay? And maybe later, I may need to update that path. But for each iteration, it gives me a path to that destination, which means that if I have n nodes in the network, I need to visit n minus one of them. Okay, so we cannot really make anything better. So it means that the larger is the network, the more time it's going to take. Okay, there's no game here, right? So it really takes time to do all those iterations. And basically, one of the things that will be the most important is to say that, okay, so I have a bunch of nodes. And you can understand that it's like, I don't know if you've seen already when you search inside a tree, is in which order should you basically inspect the nodes. And the order gives you some kind of optimization, all right? So the choice that you make will tell what the complexity at the end, all right? So anyway, so we have pretty good, how to say, complexity for this kind of the algorithm to solve it. So basically here, I'm giving one of the ways of doing this, and this is called the Fibonacci heap. So it means that we take the min priority queue, which means that if you look into the algorithm, so we start by looking at our neighbors by taking the shortest one. So we start by looking, okay, I have those many neighbors. So I'm gonna inspect first the one that is the closest to me, okay? And so once I'm done with this guy, I'm going to move with the neighbors of that next of this guy, and then move back to the next. So we have a loop here. So as you may see, so we inspect out of the list of the nodes the closest, and out of the closest, I'm going to check the neighbors of that closest one. So let's take an example just to understand how it works. So here I have network. So once again, you need to understand that this topology is known to that router because that's the one who is actually doing the computation here. So as you may see, so given the graph that I have two choices. I can go north or south. Which node am I going to inspect first? South or north? I'm probably going to go to the south because it's the shortest one. So Dijkstra are going to give us the end-to-end path to all other destinations. Given that, do we need to know the detail of the path? We don't. The only thing that I need to know is the next hop. All right. So it means that the only choices that I have is V or W. And for all the destinations, you may see that I'm just going to say if I go V or W, V or W. So you see, so I have very few choices, and any destination would be considered as a possible choice for the different destination that I have in the destination column. Okay, so let's go back to the building blocks of the protocol. First, we need to know what is the state of the link. To determine what is the state of the link, either up or down, as I said, we have a beaconing system, which means that we're gonna use special messages, which we call hello messages, and those are sent in both directions on the link by each router. And so it means that those messages, those hello messages are periodic. They are only sent to my neighbor. They are not broadcasted. Okay, I'm not sending them any further. This is just between the two of us, between two neighbors. And basically what we have a timer on each of the routers, which means that if the timer expires before receiving any hello messages, it means that either the link is down or the router have crashed, the neighbor. All right, so this is what we have here. Obviously, you may see that we have some design choices to make here. So either we want to speed up the detection, but as you want to speed up the detection, you need to increase the number of hello messages. If you increase too much the number of hello messages, in that case, you're going to use a lot of bandwidth for those messages, and what is more, the CPU to process the messages on the routers. So you don't want to increase too much number of hello messages, but you don't want to decrease them in time because you need to increase the timer in that case, and it's going to take much more time to detect the loss, right? So there's a trade-off here, okay? And guess what? Nowadays, most of the routers, they use a default value, but they cannot be like a magical value that can fit any case scenario, right? The other thing that we have now, once we know the state of the link, thanks to the hello messages, we have the link state packets, right? And those link state packets need to be flouted. And we know that flouting, whenever you broadcast something in the network, you have multiple issues, all right? The first issue is the fact that, yeah, you may have problems with loops. Look at this, when you have this message and this one gonna be sent back, and the same with the one. So basically, you can prevent from sending back a message on the incoming interface, so you don't send it back. But you may see that in that very simple scenario here, because you have a cycle in the network, the packet may come back to you. That's one of the issues. So what can we do about it, right? And not only this, those link state packets are very important because in order for your routing to be consistent, you need to make sure that all the routers then maintain a consistent database across the network. So it means that if you suffer one loss, if you lose one of those packets over a link, then the databases are not consistent, right? So what can we do about it? So the first thing, we need to make the flouting reliable. And in order to make it reliable, how can we do it? Well, acknowledges and retransmissions. So it means that whenever you flout something, you expect your neighbors to send back an acknowledgement. So you see, that makes it even more expensive. But this is the only way that actually you can guarantee that all the databases are consistent. All right. So that's to make it reliable. The other problem that we have is what about the out of order arrival? So it means that at some point I may send two packets. One is older than another. So how can I make sure that an older packet doesn't override more information that is fresh than that one? So what we do, we use sequence numbers. So it means that we have very long sequence numbers, and we use that number such as a kind of age for the messages to indicate that the higher the sequence number is, the fresher is the packet, right? So you make it long enough such as when you loop again using the same sequence number, it happened like, let's say, 2 hours later. So in the network, you cannot possibly have after 2 hours, two packets with the same sequence number still roaming around your network. All right, so sequence number are pretty powerful. And what we do as well, we're going to limit the scope of the messages by using a TTL, such as you can limit the message from going too far away, right? We are here basically located in a small domain. So yes, you may want your message to reach any router within the domain, but you don't set a TTL of 200. 200 is way too large, right? Even at the size, at the scale of the internet. Right? So those simple things here, acknowledgements, no losses, sequence numbers, you can age the messages, such as you can keep the latest one, the one that is fresher, plus the TTL, such as you avoid packets from looping forever. You cannot avoid the loops, but you can kill the packet as it loop after some point of time. Okay? Pretty simple. So when should we start flouting? As I said, there could be for any topology change. So either because you have a link or a not failure, but also if you recover them. So the link is gonna go back up from down or from up to down. So those will basically update your link state packet and you need to inform all the other routers. A topology change, so it means that the admins of some reason need the cost to be updated. And that's the reason you see that you cannot let the routers decide about the cost. Because if at some point the metric that you're using start flapping, change really often, that will create so many flouting, you're gonna have like a tsunami of flouting here. So that's the reason you wanna keep that stable as much as you can, such as you wanna limit the number of floutings, okay? Very important. And obviously we make it periodically, but as I said, every 30 minutes, all right? Just to make sure that everything is fine in the network, so you want to remove any corrupted data or whatever, but that you only needed to do it like every 30 minutes, all right? So that's when we should have flouting. But I want to remind you, okay, so if I have a network with 10 routers, how many flouting packets do I have in the network? 10 of them will initiate the flouting. So flouting initiates by each of the routers, all right? Okay, so that's a huge number. That's a huge number. But that's what OSPF needs. So I don't need only one router to do the flouting. Everybody should be flouting because you need to learn about any single link in your network, okay? All right, so let's take a few minutes in order to talk about the convergence because the convergence is really important. And once again, the convergence is I have a change, okay? The topology is changing somewhere. And you see that the change, all the routers need to learn about that change, but it takes time. So it means that it's gonna be step by step, right? So it means that at the beginning, the neighbors will be informed, then the neighbors of the neighbors, and so on. So it will spread, okay, from T0, it's going to take like a couple of milliseconds or hundreds of milliseconds before all routers are informed and all the routing tables are consistent. Right? So let's try to measure here what is affecting and what are the effects of the convergence, right? So, okay. So what we want to do, we want to reach a step where basically all the link state databases are consistent, okay? All the nodes have the same understanding and the same knowledge of the topology, which means that the shortest path to me is the same with yours for the same destination. So it means that if I'm sending this to you, is because you have the same path as I have for the destination, all right? So let's say in this network, this is what we have here, all right? So, and we're gonna focus on the source and the destination. And let's say at some point, you lose that link. There's a delay, a latency to detect the loss of the link, right? And during that period, you're gonna have a loss because of a black hole. All right, so then the hello timer will expire. But you see that the databases of at least those two routers here won't be consistent, which means that at some point, you will have one of the routers who will have a different view of knowledge of the topology, and so the forwarding will be affected, giving a loop. And if you have a loop, because the TTL may reach 0, you're gonna have losses for a different reason, okay? Then, as I said, you may have the out of order packets. So if you go and we list the reason for having this convergence, so we say the hello latency, the time that it takes to do the flouting and maintain consistency across the databases, the computation of the path, because yeah, Dijkstra needs time to recompute the path, and then updating the forwarding table. And so you see, though, those basically takes time. And during that time, what do we have? We have losses because of black holes and TTLs that expire. And we have another problem that is due to the looping, because you may see in the previous network that we have, you see that if you create a loop here, okay, so that's going to overuse the bandwidth. So it means that now if I have another traffic that goes to another node, you see that even the traffic that actually had nothing to do with that destination will be affected because of the congestion here. So it means that now we're talking about not affecting few pairs of source and destination. It may affect also other destination located somewhere else, not because the path to that destination have been lost, but because you are creating congestion somewhere in the network in between those destinations. Okay? So you see, so you're affecting even more people on the network. You can see why the loops may have an effect. Yep. Okay. Understood why we creating congestion here because of the loops. Is that okay? All right. So that's really important. And then, as I said, the final stage is the out of order packets, including when you're using UDP, because UDP have no way, if there's no sequence number, you cannot really date the packets and know that some segment or datagram is out of order. And that may be really wrong when you use voice over IP on like gaming or videos, right? And then not using TCP. You may see out of this list, there are a couple of things that I may do, right? How can I improve the detection latency? You remember that this is related to the hello messages. So what I can do probably is like, yeah, send more messages and reduce the timer, right? So I can make the timer shorter and have more hello messages such as I can react faster. So yes, I may want to change the default value of the timer. Good point. Then how can I improve the flouting? Well, maybe what I can do in my network is to make this traffic, give it a higher priority at the routers and say that if you have such packets, link state packets, please process them faster than any other traffic. So don't consider this traffic as background. This is a high priority traffic. So you may want to process the packets with a higher priority. You remember the TOS type of service? So you may want to use some trick like this to give them a higher priority at the routers. Does it make sense? Yeah, as you can speed up the flouting. Shortest path computation. Yeah, your routers may be too slow. You want to upgrade your routers with a better CPU. Well, that costs money, right? You may not have the budget for this. All right. But what you can do is maybe you can check what is the algorithm that you're using, and you may want to use a more efficient algorithm, including some that are actually incremental. So what we mean by that is like some of the algorithms that we have nowadays, they don't need to recompute all the path available, but what they can do, they can pinpoint exactly which path have been affected by a loss, a failure of a link, and they may focus on just recomputing the path for those specific destination affected by a single failure. Okay, those are much more efficient, and believe me, some routers they still run some older versions of Dijkstra or OSPF, right? And for the forwarding table, you may remember that we already discussed about it in forwarding. You may have structures such as the tries. You remember the tries we discussed about, Patricia tree, tries, and so on. So those can be updated in a more efficient way whenever you need to change one branch. You see, you can update the structure of your table if it's a tree by adding a branch or doing a rebranching for a given node. And those structure may make it faster to reorganize the structure of your table. So you can also improve it there, all right? So that's what I was trying here to list here, that actually you can reduce, but obviously you can understand that you cannot really make it void. I mean, you know, the convergence is still there, but you can improve a little bit, right? Such as if you make it faster, you have less losses, and it won't affect so much the quality of experience of your users, right? But there are ways of doing this, hopefully. Okay? All right, so that was about the convergence. Okay, so let's try to understand now why OSPF is so popular nowadays in networks. And we need to understand when you are a network operator, what do you really care about? Okay, what are the things that you really want to do? First of all, you want to do the design of your topology, right? So it means that when you connect routers together, or when you put a link between routers, it has a reason. And the reason is basically you want to be able to tolerate some link failures or some node failures. So you need to make sure that your topology is enough redundant, right? So you want to make it robust. And to make it robust, you cannot rely only on your routing protocol, right? You need to help your routing protocol by giving paths such as you can protect your network against some failures, right? And so that happens at the design of your network. Okay, so designing a network is really like black art, right? It's really hard, but it's something that you need to do very careful. The other thing, as I said, you need to be able to emulate convergence to see how fast will your network converge in face of some failures. So you need to make sure that because failures cannot be avoided, you want to make sure that it will basically, you're going to limit the disruption of your service, all right? So, and once again, that may be done by adding a new link to make it your topology more robust, but we already explained how we can do it by upgrading your routers, changing the hello timers, and so on and so on, right? So there are a couple of things that you can do. Another thing that is really important is what we call traffic engineering. And what do we mean by that? It means that you are in charge of choosing the weight or the cost of your links. And configuring those weights and the cost of the links is really important, because basically that's how you're gonna use without congestion your network. So basically you are in control of the routing by choosing the right cost and weights for the links, okay? And as I explained, doing this on the large network is NP hard. So most of the time you need to do it like almost manually or using some heuristics. Okay, so hopefully we still have a job to do here because it's not automated. Okay, and the last thing is to make it scalable. So it means that, as you may remember, we need flouting, we need databases, we need to run Dijkstra, and all of this, that doesn't make it really scalable. So in order to achieve the scalability, some of the admins, what they do usually, so let me show you this is better. What they may do is like you divide your network in multiple areas. So which means that you're gonna divide it, and each areas you're gonna run one instance of OSPF. So it means that your algorithm gonna run locally in each of those areas. So if it's a smaller area, flouting consume less bandwidth. It's faster to converge because the databases are smaller, so less memory, less bandwidth, and less CPU because you have a rather small area. And what you do then, all you're going to exchange between the areas through the backbone is you're going to exchange a summary of the paths. So it means that when you need to reach any destination that is located outside of the network, you're going to go through a default route that goes through the routers that are in charge here of that area. So routing may not be optimal because you may see that that may not be the shortest path to a given destination, but at least you do it faster, all right? So that's here a trade-off. So should you able to compute the shortest path between any pair of routers, or do you want to have locally shortest path, given that you're going to do default routing between these areas? So that's one of the ways of making link state scalable. So that's a pretty good idea, even though this is also very hard because nobody's going to tell you what is a good number of areas. what is a good size of area, and how to design the backbone network, which is here, right, to interconnect those areas. So that's also up to you, but you can scale down your problem by breaking down your algorithm or your protocol in multiple pieces, right? So this is rather something that happens pretty often. Okay, so if we try to summarize, today we talked about the link state. So once again, link state, it's you flow the information, the routing information, which is actually the topology of the network. Based on this, you have a complete knowledge of the topology of the network. This is how you can run a Dijkstra. And Dijkstra basically is about computing the end-to-end path in order to tell what is the next hop, right? So you need the complete path, such as a guarantee that the next hop is a good one. And so here you need to minimize some notion of distance, and the distance depends on the cost that you choose. So it's totally up to you. So you may want to you may want a link to look bad. All you need to do is to give it a very high cost. So this is up to you. You don't depend on the routers to decide about it. Okay, so if at some point you see a lot of congestion, the next day you can get a higher cost, and so then everybody will avoid that link. Okay? So it's easy way of controlling routing and being able to configure things. So that's the reason, because of that distance, this is how you can achieve multiple policies. And once again, the cost could be the distance, could be the capacity, could be the congestion, could be many things. All right. So the two main protocols that are using this kind of link state approach is OSPF or ISIS, giving that ISIS is the version from Cisco, but it is very similar to OSPF. On the other side, we said that we have vectoring. So in vectoring, you only know very little about the topology, right? The choice that you make is you choose between all the advertisement coming from your neighbors, the one that advertise the base distance, even though that distance may be totally fake because it's wrong. Well, any error will propagate with RIP without any way of avoiding this. Okay, that's the reason we have the count to infinity. And the best end-to-end path is actually provided as a combination of multiple next hop that each routers will calculate by themselves, okay, by doing a selection. So here, there's no distance because the only thing that we can do using RIP, for instance, is to count the number of hops. So the distance is the number of routers that you need to go through. All right, so those are the two main approaches. So nowadays, because of those problems that we just see, the most common approach is the link state. So this is a big winner. We're using static weights to make it more stable, and what is more, to be able to affect routing as we want to. So it means that I can control routing through the choice of a weight, okay? Link state, hopefully, because it's do flouting, the conversion is really fast, okay? And so we don't have count to infinity problem, or at least the convergence is much more faster. The most common protocols that we have are OSPF and ISIS, giving that we still have some use of RIP, and even before RIP, you used to have even another protocol, but those are limited to very small companies that don't really need to upgrade, given that RIP can do a pretty good job still on small networks, right, with a simple topology. All right, and nowadays we see more and more of MPLS. So it's out of the scope of this course here for bachelors. If you do in masters, maybe they will show you a little bit more about MPLS. All right. So that's it. So just to be able to introduce the next lecture. So what we discussed about today is what is happening in routing domains. And what I mean by routing domains is actually the internet, doesn't belong to the same company, right? So it means that the internet is an interconnection of networks. And usually how it works is like my network, I plug it to the internet and I start communicating with the rest of the internet. So it means that if I look at what we discussed about today, right, it means that if I look at each of those areas here, those domains, so those will be, let's say, routers and links that belong to the same company, to the same organization. and routers and links who are under the same admin entity. So the same people are administrating those routers. And when I talk about the different protocols that I have, RIP or OSPF, we run them inside those small domains. So those are ISPs, internet service providers, companies, universities. So that's where you find OSPF or RIP. So those are very small networks compared to the rest of the internet. So you're going to say, yes, but still, I need to send packets going through multiple of those domains. What am I doing? That's the reason in the internet, I have two protocols. And the end-to-end path from one client to a server result of two routing protocols working in parallel. So at the bottom, locally, in each of the areas, we have RIP or OSPF. So that's the reason we call them intra-domain routing. But on top of this, we have another protocol running. What is that protocol? For those who knows, well, it's BGP. Okay, so BGP is the top of the cream of the protocols in the internet. So this is the real protocol that runs at the scale of the internet. Obviously, it doesn't run on any single router. Otherwise, that would be impossible. So actually what is happening here is you may see that you connect to other domains using specific border routers. You can see those border routers. So basically, this is where you're going to have BGP running. So BGP is running on any routers that connects you to another domain. Okay? And the only view that I need at the BGP level, I don't need to know the details regarding each of the domains here. This is totally hidden. And I cannot request for any of those organizations to give up regarding the detail of their topology. They wouldn't allow for this, and they would be lying about it because they hide it for security reasons, for business reasons. So that's the reason we thought about, okay, how to design a protocol that actually doesn't need to know the detail. So what we do, we run BGP just by considering that those big areas, routing domains, to BGP, those are just logical nodes connected together, right? So the connection is for real because those domains you see are connected together. So this is what I have in this topology. But do I know about the detail inside each of the routing areas? By the way, we call them ASs, autonomous systems. We don't know. So what BGP gonna give us is the fact that for a given source and destination, BGP gonna decide what is the path that I should take across the domains. Within the domains, BGP doesn't have the detail. But he can tell us that, okay, if you want to reach a given destination, which is here, from that source, this is the sequence of domains, which each have a number that you need to go through. So it means that when I enter this traffic, I enter here that domain, giving that I need to exit such as I can reach domain 2. So now, from the entry to the exit, who's going to give me the detail of the path within the domain? Is it BGP? No, BGP doesn't care about this. So the shortest path here inside going to be given either by RIP or OSPF. Once I reach 2, I'm entering this domain here because I need to reach 4, because this is what basically BGP told me, 1, 2, and 4. And so it means that I'm going to ask to that domain, please, I need to exit to AS4. And so who's going to give me the shortest path to reach 4? The routing protocol running within this domain. So you see, so now that's the reason I was saying that we have a combination of at least 2 protocols, BGP at a higher level, that gives me a higher path without the detail. And now whenever I need to enter each of those domains, the local routing protocol, intra-domain routing protocol, gonna give me the path that I need to go when I transit across those domains, all right? So which means that now, and I need to clean it a little, So once again, and you see there's, I don't know why the pictures are missing, there's no computers here anyway. So you see, so basically the path that I have from that point to this one results from BGP at the top level who tells me that, oh, you need to go first 1, 2, and 4. So this is like the gross path that is given by BGP. And within each of the domains, the local path that helped me traverse each of the domains is provided by the local intra-domain protocol. So it means that OSPF or RIP only knows about the shortest path within the domain, but across multiple domains, it's BGP that gives me the information. So now it means that if I need to compute the end-to-end path, actually, the end-to-end path result, oh, it's in French, I'm sorry, 2 routing protocols that I combine together to know about any destination in the world. Understood? So next lecture, we're going to talk about BGP. Okay, so I'll let you run the animations. Okay, so routing basically is important because this is what I need in order to populate my forwarding tables. Okay, this is where I'm going to create the entries with the paths that I know. All right. So in order to be able to do the computation or the selection of the path, I need one to discover the network topology. And that's the reason I need a routing protocol, because the routers needs to discuss together to learn about the topology. Once I know the topology, I can run my algorithms, either Bellman-Ford or Dijkstra, in order to compute the paths, the routes that I will basically maintain inside the forwarding tables. Right? In order to do that, we have 2 main approaches that we discussed together. We have the link state with OSPF and Dijkstra using costs that are manually configured, or RIP, which is doing distance vector, and you optimize the number of hops for a path, and this is what you do through Bellman-Ford, and you don't need to know the complete topology. And obviously, we're going to see that in a BGP, we do something similar, but it's not a distance vector, it's what we call a path vector. So next lecture, we're going to explain what is exactly path vectoring, okay? And we see that whatever is the approach that I'm using for routing, the most important thing is the convergence, okay? Because that's what's going to affect the efficiency and the performance of your network. In case of any topology change, either a loss or a recover, or whenever you repair things. So you're going to have a transit period where your service is going to be disrupted, including losses, okay, because of black holes, we already talked about it, because of loops and TTL expired, all right, or out of order segments, which may be really wrong given the application I'm using. And what we need here, we need to make sure that the time that it takes for all the tables to be consistent again need to be as short as possible, all right? And so this is what we can do by doing some settings, including OSPF, for instance. So that's it for today, guys. We still have 5 minutes for questions.